Hi everyone, I hope everybody's having a good week so far. First of all, I just want to let you know most of you should have your tests back, and I've hopefully gone over those with you and you see what you missed from chapter 10 and 11. We have finished chapter 12. We did 12, 3, and 4 last Thursday in class, and you should be working on those this week, the week of April 18th, 19th, 20th. I don't know when you're watching this video, so hopefully if you're watching it on Monday after Easter, you've already done your chapter 12, or if you haven't, you need to get those done today and work on chapter 14 this week. I'm going to go over 14, section 1, 2, and 3 on this video. And I left you homework on the board last Thursday for 14.1 and 2, and I'll tell you what you should do for 14.3. All this will be due on April the 28th, which is when we'll have class again. Okay, let's start today by opening your book to page 572. I want y'all to take notes from this video lecture and go follow along with me in the book. So on page 572, you see it starts out with the definition of a regular polygon. Now, a regular polygon is a convex polygon that is both equilateral and equiangular. Basically, what that means, I hope you can see my notes here, is that all the angles are equal and all the sides are equal. That's a regular polygon. And I've drawn a hexagon here, which is not exactly, but you can use your imagination. All the sides are equal and all the angles are equal. Can you think of some more regular polygons? Can you think of some examples? I'm sure there's some in the book here. An equilateral triangle, a square, a regular pentagon, and it goes on and on. What about a rhombus? Would a rhombus be a regular polygon? If you remember the definition of a rhombus, it is a quadrilateral that all the sides are the same. Okay, all the sides are the same length. So, but there's no requirement that the angles be the same. So a rhombus would not be a regular polygon. Something that you might not remember is, what is a convex polygon? The definition of a regular polygon was that it was a convex polygon which is equilateral and equiangular. What does convex polygon mean? Well, back on page 730, it tells us that a convex polygon is a polygon such that every line segment that connects 2 points inside it lies entirely in the polygon. Here's an example down here of something that is not a convex polygon. We could draw a line segment from this point to this point, and does it lie inside the polygon? No, it doesn't. So it's not convex. Okay, if you draw a point, let's just take an equilateral triangle, and you draw a line segment from any point to any point, doesn't have to be on the side, but from any point to any point, it will lie inside the polygon. That's what a convex polygon is. This would not be convex. Okay, another word that you need to know is what is meant by cyclic. It was in the chapter that we skipped, and we did mean to skip that. That's something that this man whose curriculum I bought did not include. But we do need to pick this definition back up. On page 730, it tells us a cyclic polygon is a polygon for which there exists a circle that contains all the vertices of the polygon. Okay, this would be an example of a polygon that was cyclic. There's a circle that contains all the vertices of the polygon. That's cyclic. There's also something you need to know about a cyclic polygon, and that's that the opposite angles are supplementary. Opposite angles are supplementary. Okay, you'll use this in your homework. So if you still have trouble with this, go back and read on page 730 the definition of cyclic. Let's also look at what is meant by the way, Theorem 74 on page 573 says every regular polygon is cyclic. Now I'm on page 574, and we're looking at what does it mean by some polygon being inscribed, and what does it mean by circumscribed. Well, a polygon is inscribed in a circle if all the vertices lie on the circle. A circle is circumscribed about the polygon if the vertices lie on the circle. Okay, so those two words, you need to know what they mean, inscribed and circumscribed. Okay, we can use the center of a regular polygon is the center of the circumscribed circle. Radius could mean the center of the polygon to the vertex, or the distance between the center and the vertex. A central angle of a regular polygon is an angle formed by radii drawn to two consecutive vertices. Okay, so a central angle of this regular polygon would be this angle. Let's call this C. We already have a C. Let's call it O. So BOD is a central angle of this regular polygon. There's a new word here that we're going to talk about, and it's called the apothem. It's a perpendicular line segment drawn from the center to one of its sides. So this right here, O, let's call it OT, is the apothem of this regular polygon. Okay, and that's section 14.1. 14.2 wants us to look at how to find the perimeter of a regular polygon. Okay, so let's look at a regular polygon and try to find its perimeter. Just draw it with this. Try a hexagon again. When I put my arms there, y'all can't see. But anyway, here's the hexagon. I'm going to draw the radius going from the center out to the vertice, one of the vertices, and then I'm going to call the length of one side S. P will stand for perimeter, and perimeter equals N times S. You're going to use this formula when you know the number of sides, because N stands for the number of sides, and when you know the length of one side. That's what S stands for, length of one side. So if you know the number of sides and the length of one side, you can use this formula to find the perimeter of the regular polygon. Okay, so let's do a problem. Say you know that it's a hexagon and that one of the sides equals 3. How can you find the perimeter? It's really easy. You're just going to use this formula where N is the number of sides, and in a hexagon, how many sides? 6. And then the length of one side. Okay, the length of one of the sides is 3, and so the perimeter is 18. And that's pretty easy. Now we have another formula that he develops on page 580. We're not going to go through that, but he uses our trig function to develop another formula for perimeter. Y'all, I'm recording and I need you to leave, and do not come back in here.
Sorry.
You're going to use this formula to find the perimeter of a regular polygon or you can use this formula, which is for the perimeter of a regular polygon, to find other things, like maybe you know the perimeter and you want to find the radius. You can use this formula. Perimeter equals 2 times capital N times R, where R is your radius. What in the world is capital N? Well, he derives capital N using some of the trig formulas, and capital N is little n times the sine of 180 over little n. Little n is the same as it was a while ago. Little n is the number of sides. Little r is the radius. Okay, so let's do an example using this. We want to find the radius of a regular polygon when we know that the perimeter, say, of a hexagon, when we know the perimeter is 18. So let's plug in. P equals 2 times big N. So what's big N? That's this right here. So it's 2 times big N, which is little n, which would be 6, because that's a hexagon. Little n is the number of sides, times sine of 180 over little n, times r. What else do we know here? This is big N. Number of sides, we knew that. We don't know r, we do know p. So 18 equals 2 times 6 times the sine of 30 times r. So 18 equals 2 times 6 times the sine of 30, and you can use your calculator to get the sine of 30, or the sine of 30 is, I think it's 1/2. Yes. Times r. So 18. John, if you come in here again, I'm going to give you a spanking. Do not come in this room. 2 times 3, r. 18 equals 6r. So r equals 3. If I knew how to pause this and come back, I would. I think I'll try it.